Okay, this is the 8th video in the playlist that deals with drawing Lewis formulas from the chemical formula of a particular compound. And what I want to do in this video is focus on an advanced topic like I did in the last two videos. And in this video, what we're going to do is focus on dealing with compounds that have alternative structures. All right, so I'm going to be introducing the concept here of formal charge. All right, and here's the issue spelled out. A structural formula or a Lewis formula is our best guess or model to depict what the molecule looks like. In other words, what its connectivity looks like. And it works, our model works pretty well for most molecules, but there are many molecules where the model begins breaking down. And when we deal with sulfur, and so the first example that we're going to look at is the polyanion called sulfate. All right, and notice that sulfur is in period 3. So remember, your periods are the horizontal rows that cut left to right across the periodic table. So sulfur appears in period 3. And in terms of the quantum mechanical model, sulfur therefore has d orbitals that are available. It has empty d orbitals that are available to it, so that when it forms covalent bonds with another molecule, sulfur is one of the special cases that can actually expand. We call it expanding its octet. So it can have more electrons around it than 8. So what I want to do is address that issue, all right? And what we're going to do first is I'm going to ask a question the way it's asked of students quite often. And what I'm going to say, the question will be, draw the Lewis formula of sulfate abiding by the octet rule. So we're going to first draw the structure of this, all right? And following the steps, sulfur is in group 6, so it's going to be 6 valence electrons for the sulfur, and there's only one of them. And then the oxygens, there's 4 of them, and oxygen also appears in group 6, so we're going to have 6 valence electrons from that. And then remember the deal on the charge. We've got a -2 here, so we need to add 2 onto this. All right, and we see that when we do that, we're going to end up with a total of, well, so this is going to be 6 plus 24 plus 2. So my total electron count is going to be 32. All right, so we have, this is going to be our magic number. I'll go ahead and underline it in red. Now, in this case, we're abiding by the octet rule. So I'll go ahead and draw my central atom, which is going to be the sulfur, and I'm going to put my oxygens around it like this. And we'll go ahead and connect everybody. All right, and you can see here we've used up 4 electrons. All right, and we have a total of 8 around the sulfur. So in this next step, which is normally the one where we're going to put unshared pairs of electrons on the atoms, we don't have to worry about the sulfur because there's already 8 electrons around it. So let's go ahead and take care of the oxygen. So we just go around and we put in our pairs of electrons. All right, and when we're done, what you're going to see is that we've reached our magic number. There's 32 electrons here. There's literally 8 for each oxygen set, and 8 times 4 is 32. And then if you go around, you're going to see that there's 8 electrons around each of the atoms that are in this structure. So we'd be done at this point if the question had been, draw the Lewis formula of sulfate abiding by the octet rule. But here's the situation. There are other possible structures for this molecule. So if we change the question and we said, draw, and I'm going to abbreviate Lewis formula, draw the LF, which gives the best possible structure, which may violate the octet rule. All right. Now, to do this, we're going to need to utilize a concept called formal charge. And formal charge is, and I'm going to abbreviate formal charge as FC. Formal charge, let me give you the equation first and we'll talk. I'll try to boil this down into English. So the formal charge is going to be equal to the valence electrons, so the number of valence for a particular atom, minus, and then there's going to be a quantity here. It's going to be 1/2 the bonding electrons. 1/2 the bonding electrons, I'll do it this way, plus the total number of unshared pairs of electrons on that particular atom. And basically what this relationship tells us, formal charge, is it's basically giving us a sense for what the level of electron sharing is on a particular atom within a structure. All right, and what we're looking for here is a formal charge, if possible, of 0 on all the atoms that are in a particular structure. And when the formal charge cannot be 0, let's say it's a negative charge, then we want our negative charge to be on the most electronegative atom that's in the formula. And if there is a positive formal charge somewhere, we definitely want the positive charge to be placed on the atom, which is the least electronegative atom in the compound. So let's take a look at what I'm talking about. All right, so we can redraw sulfate. One possible structure would be this. All right, let me get this one done. And another possible structure would be this one. And there, in fact, are others that we can draw here. Because you can imagine in the molecule on the right here, since we doubled up electrons, we could put another double bond in this location, another double bond here. But what I want to do is start applying this idea of formal charge, and we'll start with this molecule over here. So if we calculate the formal charge on the sulfur in the original sulfate that I drew, all right, the FC for this is going to equal, all right, the total number of valence on sulfur is 6. We already figured that out. That's going to be minus, all right, now 1/2 the bonding electrons. So we go around and we count the total bonding electrons that we've got. So there's 2, 4, 6, 8 of them. We take half of that. So we're going to have a 4 here. And then this is going to be plus all of the unshared pairs that are on the S. And since there's none, then we have a 0. So you can see the FC on the sulfur in the very first compound that we drew, the one where we maintained the octet rule, the FC is actually +2 on the sulfur. Now the oxygens are all identical, so we only need to do one of them. And so the FC on the oxygen is going to be, again, that's going to be a 6 because they're in the same group actually. 1/2 the bonding, well, there's only one bond here, so it's going to be 1, all right? And then we've got 2, 4, 6 total unshared pairs of electrons. So it's going to be 6 minus 7 or minus 1. So in the very first structure that we drew, all of the oxygens have a formal charge of -1. That's good news. However, we have a molecule here that has a formal charge of +2. Now, if we come over here to this next particle, all right, I want to quickly calculate the FC for the sulfur. I want you to see what's going to happen to it as we're adding double bonds to the sulfur. So the FC here is going to be equal to 6 minus, all right, total bonding electrons. We need 1/2 of the total bonding electrons. So it's going to be 2, 4, 6, 8, 10. So half of that is 5. And then we're going to add unshared pairs, of which there are none. So look what happened to my FC. It dropped to +1. So common sense dictates that moving by adding another double bond, the FC on this sulfur here has gone to 0. All right, now notice that we can draw similarities between this second molecule here in terms of the condition of the oxygens. All right, any oxygen that's got 3 pairs of unshared electrons on it and a single bond is going to be -1. So we don't need to recalculate that. These are going to be -1. The unknown actually are the oxygens here that are double bonded. So let's just deal with that really quick. All right, deal with this quickly. Let me just fix this little typo that I had here. All right, so you can clearly see those unpaired electrons. All right, so the FC for a double bonded oxygen is going to be equal to 6 minus, all right, 1/2 the bonding electrons. So we've got 2, 4 electrons, and half of that's going to be a 2. And then we've got 2 unshared pairs of electrons for a total of 4. So notice the FC on a double bonded oxygen is 0. So that makes this guy 0 too. And each of these oxygens is -1. Now, I'm just gonna tell you flat out right now that this structure right here that I'm circling in red is in fact the best structure of sulfate. But we can prove that. And so very quickly what we're going to do is write the next option for this. And that's where we're going to have 3 double bonds going to oxygens. Now, we already know, all right, that this oxygen right here, this single bonded, is -1. And we already know that our oxygens that are double bonded in here, let me get these get those electrons in there, are all 0. All right, so that just leaves us with this sulfur. All right, and so we're going to calculate very quickly what the FC is on this sulfur. And we see that it's going to be 6 minus, all right, let's see what our total bonding is. 2, 4, 6, 8, 10, 12, 14 electrons. Half of that is 7. And then there are no bonding electrons. I mean, there are no unshared pairs of electrons, all right? So our FC on the sulfur here, after adding this next bond, is going to be -1. So this structure that we have in the middle is the best structure because we have the only negative numbers are on the most electronegative atoms that are in the molecule, and the other oxygens that are competing here have FCs of 0, and the sulfur itself, our central atom, has an FC of 0, which means that the level of sharing between the oxygens and the sulfurs is maximized to account or at least moderate their respective electronegativities. All right, so this would be the best structure of sulfate when we eliminate the need to stay within the octet rule. All right, and I'm going to go ahead and close with that.